Okay, good afternoon, everybody. This was a really tough slot. I'm really happy that I'm speaking at this slot because otherwise I wouldn't know in which talk to go. I'm not really happy that I'm speaking, but I'm also happy that I don't have to make that decision. So this is going to be an introduction to cache-friendly C++. My name is Müller, and I work at ThinkCell. So ThinkCell, we sell a plugin for Microsoft PowerPoint that is sort of the industry standard. Everybody who does PowerPoint slides for a living uses our plugin because it just makes it so much easier and so much faster to create slides. We've got custom diagrams types, a bunch of advanced automatic layout algorithms and stuff like that. We sort of hack into PowerPoint to provide a seamless experience. So there's a bunch of reverse engineering in there, and then we have like really a lot of C++ built on top of it. We have like a custom standard library that we use that has a bunch of cool stuff, which I actually maintain as my day job. And we solve a bunch of really fun and challenging problems. So if you're interested, we are hiring, and we do offer relocation to Europe in case that's something you're interested in. So this is somewhat a talk about performance, and as such, it features a bunch of benchmarks. But it is not a talk on how to properly benchmark, because I essentially did the benchmark approach the entirely wrong way around. I had results that I wanted to demonstrate, and I kept trying to write benchmarks until I had the results that I was trying to get. And this isn't really how you're supposed to do benchmarks. But I wanted to tell a story in this talk. I wanted to demonstrate some effects, so I gamed the benchmarks in such a way that I got the effects. I also picked CPU architectures in a smart way to get the results. So some of them were on my laptop, some of them were on Apple M1, just to really get good results. I'm presenting two numbers, I'm presenting two effects, but this isn't just, you really need to do your own benchmarks before you make any optimization decisions. And don't take anything I give you in my talk and just apply that blindly, measure yourself. So with that, why do we care about CPU caches? So for motivation, let's consider the task of writing a set. The standard library provides two set types. We've got stdset, which is a binary search tree, so it has the classical O log n lookup and insertion, and std_set, which is a hash table, so it has amortized O1 lookup and insertion. But we can also just simply use a std vector. And once we have a std vector, we just push back to insert elements, and then it's just an ON linear search in order to find something. We could also be slightly smarter and use a sorted std vector, and then we can do a binary search on it. So we have log n lookup, but ON insertion because we need to find the position to insert, and then shift everything over to insert, so that makes it ON. However, if we're inserting n elements at a time, we can be a bit smarter by just appending them at the end and then sorting, and this makes us n log n. And you can even do some optimizations there by knowing that you only need to sort the things that you're adding at the end, and then just doing a merge in order to put everything in sorted order. But this isn't relevant here. So let's benchmark this. As a setup, we're just filling our set containers with n random integers, and then we're just gonna repeatedly look up a random integer and measure how long it takes. And purely based on the big O complexity, we'd expect that the std another set, which would be the fastest because it says O1 lookup. Std set and std vector both have our log n lookup, so they should be behind that. And finally, we have the unsorted vector with the linear lookup. Now, if we look at the actual results, first of all, yes, the unsorted std vector, we can clearly see a linear growth. In the orange line, as we increase the number of elements, we linearly increase the time it takes to search them. What is slightly odd is that if we're at 64 elements, the unsorted linear search is actually faster than all the other set containers. So that's kind of weird. And also the O1 unordered set in green is consistently beaten by the sorted std vector in red. So what exactly is going on there? Well, and the answer lies in CPU caches. So what are CPU caches? To demonstrate, this is another benchmark. And here we're having a bunch of random data. And then we're doing a random modification somewhere in that data. So truly random memory access. We roll the dice, pick a random index, and modify something in there. And then we just measure how long it takes as we vary the size of the data. And while you might naively expect that this takes the same amount of time regardless of how much data we have, this isn't the case. As we increase the size of our data set, the time it takes, the speed we get, drops off. In the beginning, in the blue region, it's constant. So for the first couple of kilobytes, It doesn't matter how much data we have, it stays the same. But then in the green region, so from like 80 to megabytes, it drops off as we get more and more data. And then in the orange region, it drops off significantly faster as we increase the data, but then like evens out, flattens out towards the end. So why is that? Well, naively, memory access might work like this. So we've got the CPU on the left, and then all the way on the right, we've got the random access memory. And now we want to execute a bit of code. So we want to like load the value at address 2 into our register. And for that, we need to do a memory access and load the value all the way from RAM into the CPU. And then we want to load address 5, so another memory access loaded all the way into the CPU. And now we need address 2 again, so another memory access loaded all the way. Now, if this were really how your computer works, we wouldn't be very happy because main memory access is slow. It's like really, really slow. This is just some data I've got from Wikipedia. So on the Apple M1, the RAM access is almost 70 gigabytes per second. And it has a performance of 2.6 teraflops, which translates to doing operations at 10,000 gigabytes per second. So the actual performance, the main memory access is 100 times slower than compute. So if we were to get to main memory every time we needed to do an operation, we would be 100 times slower. And so main memory doesn't, so this like memory model doesn't work like that. We have caches. So the idea is we put some memory that is faster, put it closer to the CPU. It's like physically closer to the CPU, so we have less speed of light delay in there. And now when we do memory access, we leverage the cache. So we want to get address 2. It's not in the cache, so we've got a cache miss. So we put it in the cache, though, and then transfer it on the CPU. And likewise, when we want memory address 5, it's not yet in the cache, so we have another cache miss. So we load it into the cache and then put it into the CPU. But when we've got address 2 again, it's still in the cache, so we can avoid the main memory access and just directly load that into the CPU. So the smaller, faster memory close to the CPU serves as a cache, speeds things up. Unfortunately, it is smaller. So if we did a bunch of memory accesses and completely filled our cache, and now we want to load address 1. Address 1 isn't currently in the cache, but the cache is full, so we have to evict something and replace some entry with the entry at memory address 1. Unfortunately, the entry we just evicted is the one we're just about to need. Right? So now we need address 5. It used to be stored at the address we just evicted, so we've got another cache miss. We need to evict something else and load it in there. And so this might make the problem worse because now we might have evicted something we needed in the future. So the caches are really small. And to avoid going to the main memory every time we have like exhausted the cache and we have a cache miss, we have like a hierarchy of caches. Caches get bigger but like somewhat slower to access. But it's still not as bad as going all the way to main memory access every time we don't have the data. So on the Apple M1 again, so we've got like an L1 cache per core. It's between 64 and 128 kilobytes, and we can access it in about 3 cycles. Once we have a cache miss on the L1, we go to the L2. It's 8 to 12 megabytes. It's shared, so multiple cores share an L2 cache, and we can access it in about 18 cycles. There's also an L3 cache. It's shared with the GPU, 8 megabytes, and we can access it again in 18 cycles, but there's a latency of 10 to 15 nanoseconds. And only if we exhausted all of those, do we truly need to go to random memory access. It's big, like 16 to 32 gigabytes, but it will pay an additional 100 nanoseconds to go there. And this explains the benchmark. So in the blue region, our data entirely fits in the L1 cache. It didn't really matter what we accessed. It's always in the L1 cache, so the speed stays the same until we exhaust the L1 cache. Once we exhaust the L1 cache, we lose a bit of performance, and in the green region, it entirely fits in the L2 cache. However, as we increase the data further, the probability that we hit data that is already in the L1 cache decreases. So we have more and more L1 caches while we're in the green region, so the speed drops further and further, simply because we have more and more L1 cache misses. And then when we go in the orange region, we've exhausted the L2 cache, and again, so we pay a penalty for that, and as we go on, the probability of an L2 cache hit also decreases, simply because we have more and more data, and so it flattens out. And if we continue measuring, in the end, we will have the speed of main memory access, because essentially every time we get a random number, it's and then cache miss on all levels, and we go to main memory access. Now, every time we cache something, we have to worry about cache invalidation and stuff like that, and in particular, what happens when we write to an address that is currently in the cache. There are two models. The simple one is every time we write to an address that is cached, we update it both in the cache and also in main memory. This is called a byte-through cache. However, we have to pay for additional memory accesses in this model. So a smarter model is a write-back cache. There we only update the cache, and then we only update main memory once the cache gets evicted. And because of this being a bit smarter, CPU caches are usually write-back. This, however, will have fun consequences once we talk about multiple threads. Now, the takeaway is main memory access is slow. It's like really, really slow. And so we can avoid main memory access by using caches. Caches are faster, closer to the CPU, and we cache frequently accessed values in there. However, the caches are small. So if you want performance, you need to ensure that as much data as possible fits into the cache. So how do we make efficient use of the cache space? So here's an example. We have a bunch of ages of people or something, and we want to compute the average age. So I'm using a strongly typed integer for our age, and then we just loop over all the data, compute the total, and then the average. Now, we want to optimize this and make sure that we use as much data as possible in our caches. And one simple way to do that is to simply use a smaller type. If we use an int as our age, we need 4 bytes, but we can store ages between -2 billion and +2 billion. And like people don't get that out, right? So we can go to a short only using 2 bytes, or even an unsigned 8-bit integer, only 1 byte, and then we can still represent all ages of people in our data set. So let's benchmark it for various sizes of ages. And as we can see, the short beats the int. So we're faster, simply by making sure that more of our data fits in the cache. But if we then go to the U&AT, we are still faster than the int, but we're not as fast as the short, even though more of our data fits in the cache. So what's going on here? And the simple answer is, on this CPU, the arithmetic on the U&AT is apparently slower than the arithmetic on a short. Right? So again, I want to reiterate, always measure before and after optimizations, because even though you're improving one metric, you might lose on something else. Now, optimizing the type size for primitives types is quite simple. Just you pick a smaller primitive type, like signed char or short, use float instead of double, and specify the underlying types of your enumerations. It defaults to int, and you will not have like billions upon billions of entries in your enum, so you can use a smaller enumeration type there. And because you're not doing arithmetic on it, it like shouldn't affect the performance that much. Instead, you just save some space, and therefore space in your cache. Now, one thing you have to be careful about is about the 1-byte integer types. So first of all, I particularly said use signed char. Because there are actually 3 distinct 1-byte integer types. There's signed char, which is int80, there's unsigned char, which is uint80, and there's plain char. And plain char is a distinct type with implementation-defined signedness. So on some architectures it's signed, on some it's unsigned, but nevertheless it's a distinct type. And this is a special thing for char. Normally when you put signed, like a signed int and a signed short, that's just the same as int or short, so nobody writes it. But for signed char, this is actually a distinct type. And I have no idea why this is the case. But anyways, we've got 3 distinct 1-byte integer types. And when I said 3, I obviously meant 5, because we also have char80. Char80 is a type meant for UTF-8 text. And then we have std_byte. This is an enum class that's meant to be used for raw memory accesses. Now, all of those are 8 bits. All of those are 1-byte types. Let's benchmark them. So this is a function that just takes a 1-byte type and increments it. And I have to byte the increment a bit ugly because byte is an enum class and it doesn't have operator ++. So I just have to cast that to an int, do the arithmetic, cast it back, so it works on all types. But like this all boils down to the same CPU instructions, so it doesn't really matter. And if we benchmark our various types, we'll see that all of them have the same performance except char80. Char80 is faster. And that's kind of weird. So does that mean that you should use the UTF-8 type to do 1-byte arithmetic? Maybe, because it has one advantage. So the reason char80 is faster has nothing to do with CPU caches, has nothing to do with the actual assembly instructions used to manipulate them, and all to do with the optimizer. And so C++ has this rule called strict aliasing. If you have an object of some type that lives at some memory access, you can only access it using a pointer of some compatible type. So if your pointer has the appropriate type, same as the object, it works. If it has the signed or unsigned type, it works. Or if the pointer is a pointer to char, unsigned char, or std_byte. That means that if you have a pointer to char unsigned chars.byte, it can point to anything in memory, not just to objects of that type. C has a similar rule. C, however, doesn't care as much about which specific flavor of char you use. It just allows char, unsigned char, and signed char. And usually the optimizers don't differentiate between C and C++, so they all assume that a char pointer or a signed char pointer can also alias anything. Now what this means for generic code is that if T is a non-aliasing type and we modify data I, this can only modify other T objects. So that's all good. However, if you have an aliasing type, then the modification of data I may modify anything in memory. And vector T is something that is somewhere in memory. So the optimizer has to assume that modifications to data I may modify our vector. And in particular, it may modify the size of the vector. So in the loop, the data.size, if it's non-aliasing, the optimizer can see it's not changed, and it can heist that out of the loop and doesn't repeatedly call it. But if it's an aliasing type, it has to assume that the assignment could potentially modify the size. And so it has to reload the size every time we're going over the loop. And this explains the performance benefit that we get with the non-aliasing char 80, simply because the optimizer was able to write it better. So of course, you can still use char and signed char or whatever. You just have to make sure that you apply the optimization yourselves. So now we've manually hoisted it out of the loop, and now the data I assignment can no longer modify it because nothing took its address. So the optimizer is just free to put that in a register and never reload it. Or of course, you could just use the range-based for loop. And in either situation, you will now finally have the same performance. So again, benchmark, be really careful when doing any kind of optimization, and especially about the one-byte types because of strict aliasing. It's really unfortunate that they have this property and that we don't have one-byte arithmetic types that we can just use to do arithmetic without having the optimizer mess with us. Now, if you want data that's smaller than 1 byte, you could use bitfields. So here we've got a widget. A widget can be enabled, it can be visible, and it has one of 3 states. And now if you put all of the members in a struct, widget is 3 bytes because a bool is 1 byte, and the enum with the underlying type is also 1 byte. However, we don't really need 3 bytes because we have 1 bit for enabled, 1 bit for visibility, and 2 bits to represent the state. So we can use bitfields and just say behind the colon, this is how many bits we actually need, and then the compiler can pack them together in 1 byte. So now size of widget is only 1 byte, and we even have bits to spare to put additional flags in there. However, now the access is slower, because every time we access it, we load a byte, and then we mask off the bits we don't care about. So any effects we might get from having more widgets in our cache can be completely negated by the actual overhead for the access, so we have to benchmark that. One optimization that's usually free, though, is simply reordering the members. So here we've got a message. It has an 8-bit type, a 32-bit length, and an unsigned char data pointer. It also has a 16-bit checksum. On the 64-bit system, if we add off all the sizes, we end up with 15 bytes. So we have 15 bytes of meaningful information in our struct. But the actual size of the struct is 24. And the reason for that is alignment. So the alignment is simply a requirement on types, and it places restrictions on the address that can be located. In particular, the address has to be a multiple of the alignment. So if you have a 1-byte aligned object, like our uint 80, it can be put anywhere in memory. But if you have a 2 or 4 or 8-byte aligned object, it only has to live at addresses multiple of 2, 4, and 8. Now, if you have a struct, you need to ensure that all the members are properly aligned. So first of all, you pick the alignment for the struct, and this is simply the largest alignment of any of the members. And then, as you place the members down in memory, you have to ensure that each member is properly aligned by putting padding bytes. So you have to ensure that the offset of each member starts with a multiple of the alignment, so you put in internal padding bytes to make sure of it. And then at the end, you have to put in tail padding to make sure that if you have an array of struct objects, you want to make sure that each object in that array is also aligned. And so the alignment of the struct essentially has to divide the size, otherwise your array objects get misaligned. So you add tail padding until the size is a multiple of the alignment. So for our message in this particular order, that means that we start our uint 80 at address 0. Then we need to introduce some padding until we find an address that is divisible by 4 for uint 32t. Then everything works out. But if we reach byte 18, that is not a multiple of the alignment, which is 8. So we need to introduce some padding bytes at the end to make sure it's a multiple, and it works. However, if we simply reorder the members of our message from largest alignment to smallest, then we get the most optimal padding. In this case, it's only one single padding byte at the end to make sure that the entire thing is aligned to 8. So this is just essentially a free optimization in many situations where we now have a 16-byte message instead of a 24 one, and we can fit more of them in our cache. But we can leverage alignment even further. So if we have a pointer to t, because t objects have to be properly aligned, the pointer always points to a multiple of a line of 2. That means that if you view it in binary, the lower bits are always 0, because that's what it means to be a multiple. Right? So if you have an object that has to be at an even address, it only has to, the last bit is always 0. Right? And if it's divisible before, the last 2 bits are 0. And because we know they're 0, we can use them and store whatever information we want in them. So for example, suppose you're having some sort of DOM or whatever, and it has like containers or texts in them. And now you will need a type that needs to store either a pointer to a container or a pointer to text. And the naive way to do it is you store a boolean and a void pointer, and then you just cast to the appropriate one in the accesses. And this type has 16 bytes, which is really unfortunate because the actual data it stores is like an 8-byte pointer and 1 bit. But we can't store 1 bit, we have to store 8 additional bytes to make the alignment. And this makes me really sad every time we blow up like 8 bytes just to store 1 additional bit. Like, that's really unfortunate. But if we can assume that both text and container objects have an alignment of at least 2, we have a spare bit in our pointer. So by just storing a single UN pointer, so like an integer representation of the pointer, we can say impl is the pointer to the object with the last bit set to 1 if it's a text. And so it's a container if that last bit is 0. And so when we get it as a container, we just cast it, get it as a container. But if we want to get it as text, we have to mask off the last bit because it's 1, and the address has to be a 0 in there, and then we cast it to a pointer. And now we've stored everything using only 8 bytes and avoided the override. So if your types are smaller, more of them fit into the cache. So use short instead of int, use float instead of double, specify the underlying type of enumerations, consider bit fields, reorder your struct members to avoid padding, and consider using tricks like the pointer alignment bits to like really avoid a bunch of padding to store additional bits of information. However, all of this means that the access of the data now is potentially slower, so you have to benchmark it and see whether you really gain anything out of it. Now, if you've been paying attention, you might be wondering, why did that actually help? In the average age benchmark, when we made the age type smaller, why did that actually help? We're only accessing every address once, right? We don't go over the data again. So we're only accessing everything once. So why does it matter that more of them fit in the cache? Everything should be a cache miss anyway, because we haven't accessed the data before. And also, the cache so far doesn't explain why std vector was faster than stood on under map in the motivation. And to look into why that is, let's not benchmark only random access, so like in the first one, but also linear access both forwards and backwards. And to make the comparison fair, in both sequential accesses, I'm still computing a random number and throwing it away, just so we pay for that every time. And now we see something interesting, because if we do sequential access, we have the same performance no matter the size of our data. And only if we do truly random access do we drop off. And the reason for that is simple. When we access some address x, we usually also access the next address and the address after that. Right? And the people who design our CPUs know that. So they introduced a prefetcher. It's something that preemptively loads addresses into the cache if it's likely that we're going to access them in the future. Right? So in a sense, it sort of like predicts the memory access pattern that we're going to do and makes sure that we won't have cache misses by preemptively loading. But this isn't all. So in this benchmark, I again have random data, and I'm accessing it randomly, but I'm accessing a random chunk at a time. So I pick a random start address of a chunk, and then I access all the indices of that chunk in a random order and do something with it. So here we're accessing random chunks from our data, and we're accessing data within the chunks randomly as well, but like still only a relatively small chunk size compared to the entire data. And now we measure this by varying this chunk size and see what we got. And the result is that as we increase our chunk size, the performance goes up. However, it goes up slower. So if we look at the forward difference, we see that if the chunk size is already in the 400 bytes, making it slightly faster doesn't get us as much performance as initially, right? So as we increase the chunk size, it has diminishing returns. So why do we have this effect? Well, and the answer is main memory access is slow, and so while we're accessing main memory, it doesn't really make sense to only access 1 byte, right? So we access an entire cache line of data. A contiguous byte range, usually 64, 128 bytes, is accessed into the RAM and loaded into our cache. So in this model, the cache line size is 2. That means if we load our address 2, we not only load address 2, but also address 3, put both of them in our cache, and then set the register with the value at address 2. Likewise, when we do address 5, we don't load just 5, but the entire cache line. And in this case, the cache line consists of addresses 4 and 5. So we load both of them into the cache and send the address 5 to the CPU. And now when we need address 3, even though we've never actually accessed address 3 before, it already happens to be in the cache because we've fetched the entire cache line. And this was sort of demonstrated with our chunked access. As we did the chunked access, when we had only a really small chunk, we loaded an entire cache line, but threw away most of the information. And as the chunk size went up, we used the cache lines more and more efficiently. So the CPU not only caches it, but it also wants to minimize memory access, and it does so by preemptively fetching entire cache lines. It learns our memory access pattern and prefetches it. And so if you want true performance, you want predictable memory access patterns that have a high locality. And one easy way to achieve that is to use cache-friendly containers. So we want to leverage prefetching and cache lines. What this means is that we want predictable access patterns. We don't want pointer chasing. So if we need to load dereference a pointer, the prefetcher has no idea what we're just loading because it has to know the value of the address first. Instead, we want sequential memory access. Just access the memory sequentially, and then the prefetcher can help us. We also want to make sure that we have high locality. So that means we want to minimize the size of our types to make sure that more of them fit in a cache line. And we also want to, on the flip side, make sure that data we don't care about lives somewhere else. And so we don't want to waste space in our cache line, so data we don't care about shouldn't be in our cache line. And std vector of t is a prime example of cache-friendly container, because it has a bunch of values, and they all live contiguously somewhere in memory. So we don't have any metadata that wastes space in our cache line. We just have a very contiguous memory layout, and as we iterate over them, we iterate over it sequentially in memory, so the prefetcher is on our side, and everybody's happy. And similarly, like std array, also contiguous in memory, in-place vector, and everything else where you have contiguous memory access. On the opposite spectrum, we have std list. Std list is the linked list of nodes. So each node consists of the value and a pointer to the previous node and to the next node. So first of all, we don't really care about the pointers as the user of the std list, so they just waste space in our cache line. And then also, as we iterate over them, the nodes can be in any order in memory, so the prefetcher also can't really help us, because we're just following pointer around as we iterate. So this isn't really cache-friendly. On the middle end, we've got something like std of t, which is logically a vector of pointers to arrays. So we've got contiguous blocks. So within a block, we are contiguous, no metadata, so the prefetcher is happy, and only when we switch from one block to the next do we have to do a bit of pointer chasing. So if the block size is big enough, the transitions between blocks don't really matter that much, so we're still cache-friendly. But if the block size is too small, then we just have a linked list and where we just follow pointers. And it's unfortunate that in at least one standard library implementation, the block size is too small to get any meaningful cache benefits. So I wouldn't necessarily rely on std. It's in theory a useful container because it provides pointer stability of the elements. As you add more data, the addresses never change. But if you need it, then you should probably roll your own because you can't rely on the standard library version having a big enough block size. What's also not cache-friendly is the standard library implementation of map and set, because it's a binary search tree. So like the linked list, we have nodes with left and right pointers, and then we have to do pointer chasing. It's, from a memory layer perspective, it's exactly like a linked list. It's just that the pointers have different semantic information. But either information, the prefetcher can't help us. We're having metadata in the cache line that we don't care about, so we're wasting valuable space. And really unfortunately, unordered map and set are also not cache-friendly. This is because they use closed addressing, which means that it's fundamentally an array of buckets. And each bucket is a single linked list. So we're having a vector of node pointers, and each node pointer has the key value pair, and it points to the next one with the same hash value. So when we want to do a lookup, we compute the hash value, we pick a bucket, and then we follow the pointers until we found the key value pair of our thing. Right? This isn't great for the prefetcher. This wastes space in our cache line due to all the metadata, so it's not very cache friendly. And that is why in our benchmarks, for small enough values, the sorted vector beat the O1 thing, because it's a bit better for the prefetcher. Now, this is unfortunate, because you can make hash tables faster. Right? You just have to use, for example, open addressing. In open addressing, you're just having like std vector, you're having a flat list of elements, and then when you hash, you go to some random, to like the appropriate bucket, check whether it's the value you care about, and if it's not, you look at the neighboring ones. Right? And that is now really cache friendly, because you don't have any pointers, you just look at neighboring addresses in some space. So they can be a lot faster. But unfortunately, the standard library doesn't provide an implementation. So, in general, you should prefer containers that use big contiguous chunks of memory, because that is way better for your caching effects. It's more cache friendly, the prefetcher will help you, you don't waste your cache line with unnecessary metadata, you're just having the data you care about. And so in almost all situations, use std vector. You can also use some implementation of std of t if you care about the properties it has, and you can use hash tables with open addressing, because all of those are cache friendly if they use the big contiguous chunks of memory. Unfortunately, this isn't all. Now, one thing, after I took those measurements, I looked at the data sheet of the CPU, and the cache size I measured for the L2 cache didn't match up with reality. So I somewhat arbitrarily picked the line after 2 megabytes, but the reported cache line was 4 megabytes. I could say, okay, maybe the bar next to it is also part of the green regime, but definitely the drop-off happens before we reach 4 megabytes. So what's going on there? Well, the simple answer is code is data too. The CPU instructions your program consists of also live somewhere in memory. And main memory access is slow. Therefore, it's avoided using faster caches. And these are the instruction caches. So on the L1 level, you usually have separate instruction caches compared to the data caches. But on the L2 cache, they're usually unified. So you have one cache to both cache the data that your program operates on and the program itself. And therefore, the measured L2 size was smaller because some of the L2 cache size is used up for the actual program we're executing. And now, the fact that code is data means that the code itself also has weird caching effects. And we can create really contrived examples to demonstrate weird caching effects of code itself. So this is a silly example. We have a bunch of data, like random data, and we're summing it all up. But if we're having a 0, we're doing 64 separate increments. Now, the condition that d0 is rarely true because it's like truly random data. But if we do, we have 64 separate increments in there. So the repeat 64 is just a macro that expands the expression 64 times. And then we could do it in one of two ways. We could do the sum first, and then we have the if, and then we do our increments. Or we could do our increments, if we're 0, and then we do the sum. This doesn't change anything in the result. It's just a choice of writing in the if first or writing the if second. Now, who thinks this version, where we do the sum first and then our 64 increments, is faster than the second version? Okay, one person. Who thinks this version is faster? Okay, one person, but a different person. Who thinks it doesn't matter at all? Okay, you're afraid to raise your hands. Okay. So it turns out that if you use an Apple M1 and you use the high-performance cores, this version is faster. It's significantly faster. If you do the sum and then the increments, you're at 2 gigabytes per second. But if you do the increments and then the sum, you're at over 8 gigabytes per second. Just because of the way your actual CPU instructions ended up being living in memory, like just how the compiler meets the assembly of those basic blocks, just caused a massive performance difference. Just because the cache lines are differently, the alignment is differently, like something changed in the benchmark that caused a weird performance gap. I've looked into it a bit why it's such a drastic difference, but I couldn't really see anything. So if any of you have ideas, talk to me after. But the fact is, your program lives somewhere in memory. Main memory access is slow, so you've got caches. So just like you can have cache-friendly data access patterns, you also have cache-friendly code access patterns. So the cache-friendly data access patterns, you want to access your data in linear order. And the equivalent for code is you want instructions that execute one after the other. That means you don't want any branches that jump you to an entirely different location of your program, right? So for example, if you have a function call and your function lives somewhere else in memory, the first time you call it, that might be a cache miss, that might be slow. So if you're having a hot loop in there, you want to avoid that. Similarly, for the data, you want to avoid pointer chasing, because that is really bad for the prefetcher. And the code equivalent to that is an indirect jump. So if you call a virtual function or you call a function pointer, the prefetcher don't know what it is. It can't really prefetch it. So this is going to be a cache miss the first time you do it. Similarly, you want to minimize the size of the data, so you use your cache lines and your caches more efficiently. And likewise, when you're doing a loop, you want to do as little as possible in the body of the loop. And that way, you fit as much as possible into the cache. So as a consequence, you don't only want to design your data in a way to keep caches in mind, but your entire program, because the code itself also matters. And one way to do that is to follow data-oriented design. Now, there's a surprising number of data-oriented design talks at this conference, which I didn't know when I submitted this talk. Funny how that worked out. So data-oriented design is sort of classically contrasted with object-oriented programming. So in OOP, you focus on objects. These are sort of domain-specific abstractions. Whereas in data-oriented design, you focused on algorithms, which are your data transformations. So you have some data, and the goal of your program is to transform some data. So this is what you focus on. In OOP, you have smart objects that encapsulate both data and behavior. So you've got classes with member variables and member functions. Whereas in data-oriented programming, you just have the algorithms that operate on dumb data, right? Your ints don't have member functions, so to speak, right? And then if you want to have like different flavors of things, in OOP you use like base classes, and so you've got like collections of pointers to base classes. Whereas with data-oriented programming, as we'll see, you'll have multiple homogeneous collections of the different data you operate on. So one example, in OOP, let's say we want to work with people. So in OOP, you design the objects first. That means you have a person class, persons have names, they have an age, so you write getters for the actual member thing and constructors and whatnot. And then you have a vector of people. And then you operate on that. So for example, we can write a function that computes the average age, given all our people, and a function that gives you the name of the oldest person, given all our people. Now with data-oriented design, you start with the algorithms. So what's the algorithms that we want to write? Well, we want to write a function that takes something and gives us the average age. Now what does it take? In OOP, it takes the entire people. But like, we don't really care about the people. We just want their ages, right? We don't need their names in order to compute the average age. So in data-oriented design, you would write a function average age that takes the ages of all of our people. Similarly, we have an algorithm that gives you the name of the oldest person. So what's the data it needs? Well, it needs the names and the ages in order to do that. So it makes sense to split it into two functions. One that gives you the index of the oldest person, and you can do that by just getting the ages. And then one that given all the names of all the people and all the ages. So we assume that they are sort of the same size, and like the 0th object in both of them represents one person, right? And then we compute the index of the oldest person, and then we return the name of the corresponding entry in the other vector, right? And this just is sort of the data that we need to implement it. And so we're putting the data first, and we ended up with this. And what we've seen are two very different data layout approaches. So the first one we've seen, that is called array of structures. So you've got a struct that has some records, in this case name and age, and then we've got an array of those, or in this case a vector. And this is our people. Whereas with the second approach, we ended up with something called structure of arrays. So person no longer exists as a thing, it's merely an index, so we can represent it as like a strongly tapped index. And then we've got like all the data they make up, so like all the names of all the people and all the ages of all of those people. And if you do OOP, you usually use an array of structures because your struct are your objects and OOP is about objects. And with DoD, you just use whatever works for the algorithm. So if you often need to work on both age and name, then it sort of makes sense to keep them together. But if you sometimes only work on one of them, then it makes sense to split them apart. And if you look at the memory layout, if you have an array of structures, we have the name, the age, potentially with like padding bytes in between. And this gives us efficient access to individual rows if we view it as a database. So we can easily get all the data related to one person. Whereas with the structures of arrays, we first have all the names and then all the ages. And this gives us efficient access to individual columns, right? So we can very easily write programs that operate on all the ages without caring about the names. And this matters, Because if you only care about the ages, if you use the array of structure approach, your cache line is being wasted on all the names. Right? You don't need the names if you just want to compute the average age. But you still have to load them, they still occupy space in the cache line, and performance drops. Right? So if you actually benchmark it, so we've seen the benchmarks for the ages of various sizes, and whatever size for the age we pick, person is significantly slower than all of them, which is no wonder, because we're wasting precious cache line space on storing the names, even though computing the average age never actually cares about the name. Right? So this data layout is just less efficient in this particular example. So another classical OOP thing is, so we have a bunch of shapes, and we want to operate on the areas. So we design a class hierarchy where we've got the shape-based class with a pure virtual function, and then we have our circles and our squares, which derive from them, and override the area function with the appropriate formulas. And both circle and square also store the relevant data, like the side length or the radius of the things. And now we want to write a function that computes the total area, so it gets all of our shapes. As vector of unique pointers, because we have to put them on the heap, because the size matters, and then we just sum over them, call the virtual function, and sum it all up. In data-oriented design, we design the algorithm first. So algorithm is a function, total area, that returns a double. What does it take? Well, we've got circles and we've got squares. So it takes a bunch of circles and squares, and it can be either one, so we use the variant of circle or square. And in this case, circle or square are just structs that store the relevant member thing. There's no base class. And yes, what if at some point we might have a triangle? Well, then we get to it when we get to it, right? Like, unless you already know that we need extensible in the design, don't worry about it. Just focus on the problem that you're actually having at the moment. So in this case, we're having circles and squares. So we write a function that takes circles and squares. However, if we only take circles and squares, let's just write the function so it operates on circles and squares, right? So let's give it all the circles, all the squares, and write a function that sums the area of all the circles, then sums the area of all the squares, and adds the two together. Right? So these are sort of three different representations of heterogeneous data. We've got the box data in the classical OOP sense. We've got a vector of unique pointers to shapes. And this is essentially a vector of pointers. And then each of the pointers points to either a circle or points to a square. And if we iterate over them, this is really bad for the prefetcher because we follow a pointer every time. It has no idea about points, can't really help us. And we're also wasting entire cache line space on the pointers. The variants are a lot better because we're storing them inline, but still we've got this tag in there. So everything has a tag, which is just 1 bit, but probably it gets blown up to 8 bytes to account for proper alignment, which is really unfortunate. So if we just use two different vectors, we don't need to remember a tag, because we know the first vector has all the circles, the second one has all the squares, and then also when we iterate over them, we don't need a branch, because we first iterate over all the circles, and in this case we use the formula for the circles, statically known, no branch needed, and then we iterate over all the squares, so we need the formula for all the squares, statically, no branch needed. And so it's unsurprisingly that the last representation is significantly faster. Right? Just having two separate vectors, one for the circles, one for the squares, and then we compute the area, that's faster than using the variant or the pointer. And in a nutshell, this is about data-oriented. This is the idea behind data-oriented design. Right? You design an algorithm that transforms data. You start with the algorithm and you think about the data it needs. Right? And you should also write functions that operate on n elements, not single ones. Right? Don't write a function that returns you the area of one shape. Write a function that takes all the shapes and gives you the total area, because you have more than one shape. Right? And it doesn't really make sense to split it up into individual objects. And then once you write the loop, you sort of push the loop into the function, and that's a lot nicer for the optimizer, gives you a better performance. Memory layout-wise, if you only care about the subset of the data, only put that data in the array. So use the structure of arrays, only have the array of the data that you actually care about, and have all the data living somewhere else, and then only access it when you actually need it. And if you have a variant or something, just use multiple homogeneous arrays, right? Like if you have something with a Boolean member, and then based on the Boolean in the loop, you do this or that, that's usually a red flag. Just split it into two separate arrays, one for all where the Boolean is true, one for where the Boolean is false. You avoid the branch, and you don't need to store the Boolean, because we just have multiple arrays where you need to do that. And that way, you truly leverage caches, and you can have big performance gains. So far, we've only looked at single-core processors, so let's look at multi-core processors. And let's say we want to do a parallel fold. So a fault algorithm is something like a sum or an accumulate, right? We have a bunch of data and we want to sum it all up. And the way to parallelize it is a pattern that looks something like this. So we have a thread pool where we can execute work. It has some number of threads. And what we do is we create an array where we store all the local results. So the results of each thread separately will be stored at some entry in that array. And then we submit work to the thread pool, and each work sort of gets the thread index it's running on. It gets the appropriate slice of the work, so the subset of the work it works over, does the operation. So in the case of like summing elements of an array, it would take a subrange of the array, sum it all up, and then store the result in the local result of each thread, right? And this doesn't require any synchronization because each thread has a different index, so we never access the same elements of the local results array from different threads. And also, we don't modify the work. And if we were to modify the work, each one gets a different slice, so no synchronization is needed. And then once the thread pool is done, all the threads did their slices, we do a second fold over all the local results to get the single final value, the final sum of the array. So this is a really common pattern to parallelize fault algorithms. And I've written a benchmark where we do a really silly parallel fold, which is we want to accumulate a bunch of Fibonacci numbers. So this is a recursive Fibonacci implementation, just because it's a really easy way to, with relatively few lines of code, create a bunch of work for the CPU. Because it's like famously inefficient way to compute Fibonacci numbers. It just blows up exponentially, but this is what I needed. I just wanted to do a non-trivial amount of work per thread. And directly accumulates them all up in this result output parameter. And then we've got our benchmark codes, where we've got the local results of each one, and then each thread sort of sets the local results to 0, and then I'm just doing something, so in this case, it's just repeatedly accumulating the first 20 Fibonacci numbers. And note that as we increase the thread count, each thread does fewer and fewer fewer share of the work. So as we increase the number of threads, we should get more and more speed up because we're like dividing the work between multiple threads, and they all work in parallel, so we should get a speed up. However, if we actually run the benchmark, it doesn't scale at all. In fact, as we increase the number of threads, our performance even goes down. So if we use 4 threads, we are less fast than if we just had a single thread, which isn't what you see when you want to parallelize things. So why is that? Well, if you have multiple cores, the caches are only fast because they're close to the core. So if you have multiple cores, each core has its own L1 cache. That means if you modify entries in one core's L1 cache, it has to invalidate that cache entry for all the other cores as well. Otherwise, they would read stale data. And this is also where some of the atomic memory models stuff comes in. However, the CPU caches operates in granularity of cache lines. So it doesn't modify only the entry, it like invalidates the entire cache line. So in our case, we are having thread 0, which does a write at the local address at index 0, sets it to 0. This invalidates the cache line. So the thread 1 read of the neighboring entry in the array is a cache miss. Even though it might have been cached, even though it never was modified, it's still a cache miss, still has to go to main memory because the cache line was invalidated by the modification. And this is called fault sharing. Fault sharing is the cache invalidation due to modifications of unrelated data in the same cache line. And this is what happened in our example, right? We have the local results and we keep accumulating Fibonacci numbers on it. And every time we do, we invalidate the cache line and all the other threads have to like reload it from main memory or something, right? Like it really tanks your performance, you want to avoid it. And one way to avoid it is you make sure that each local accumulator lives in its own cache line by just accumulating some padding space. So we get the alignment that we need. So the standard sort of provides access to the cache line using hardware-destructive interference size. I'm not sure why they didn't call it cache line. Also, it's sometimes wrong because it's just a compile time constant that's being set, and it might not always be set properly for your target, so you probably need to roll your own. But like in this case, it worked. So you get the alignment, and then you don't only align, get like local results for each how many threads we have, but like enough for the alignment. So now you essentially allocated thread count many cache lines. And then when we access it, we modify the first value of each cache line. And so when we don't invalidate the cache lines that the other threads are using, because now each local result lives in its own cache line. And now when we actually run the benchmarks, we get the performance that we expected. So as we increase the number of threads, it actually scales and we get faster and faster performance. Of course, in this particular example, there would be a far easier solution. Just use a local variable, accumulate in the local variable, and then only write to the local results at the very end. Now, the last one still suffers from fault sharing. However, because it only happens once at the end of the benchmark, it doesn't have a big performance impact, and we still have the scaling behavior, where as we increase the number of threads, we actually get faster. And so every time you're doing multi-threading, keep fault sharing in mind. It's really, really devious. Like, if you have data that is used by different threads at the same time, put them in different cache lines. Even though it's not a race condition per se, you should view it as if it was a race condition, because it tanks your performance. Of course, the flip side is still true. If you have data that's used by the same thread, put it together in the same cache line. That way, you don't have to worry about the performance. Then to conclude, this was an introduction into CPU caches. They're smaller, faster memory that you use to avoid accessing the slower main memory. The cache line is the smallest unit of data that is transferred between main memory and the caches. And to make cache misses less likely, we have the cache prefetcher. It predicts memory accesses and preemptively loads the data into the caches. When dealing with multi-threading, we have to keep aware of fault sharing, which is cache invalidation due to modifications of unrelated data in the same cache line. And also remember, code lives in memory too. Code has caches, code has cache effects, not just your data. To truly leverage the CPU caches, we want to have cache-friendly data access patterns. We want to access it in linear order, so the prefetcher helps. We want to avoid pointer chasing, so the prefetcher can actually do its job. And we want to minimize the size of the data, so we make as much use of the cache line as possible. Don't put data in there that we don't need. And likewise, for the code, we want to avoid long branches. We want to avoid indirect branches, indirect jumps. And we want to minimize the size of the hot code, so our loop is really efficient. And also, remember, data used by different threads at the same time, put them in different cache lines to avoid fault sharing. And if you follow that, you did the first steps to writing cache-friendly C++. You're writing code that actually leverages the CPU memory effects and is potentially a lot faster, but make sure that you benchmark it so that the optimizations you're having are actually optimizations and don't make it worse. Thank you. Questions, thoughts, comments?
You often have code that moves between single-threaded and multi-threaded, because it seems like following this sort of design, you have to redesign the code every time you want to make that sort of paradigm shift, as opposed to having a function that you could call as thread state that could be called in a parallel environment and could be called in a single-threaded environment. How do you handle a thread state function being able to be written to be performant in both cases, or is it not possible?
So what do you mean by following this design? What exactly?
So I think you were suggesting that the memory layout should be different depending on if it's multi-threaded, like if you're accessing data in a multi-threaded way and in a single-threaded way. So if you've got a function that's supposed to be thread state that can be called in both, that performs some function, it seems like it'd be impossible to satisfy both.
So the problem only happens if you're modifying some data. Like if you don't do modification, fault sharing doesn't happen. And if you have a single-threaded function that modifies some data, and then you want to parallelize it, and you don't change the data layout, then yes, you could suddenly have fault sharing, right? However, what you usually do is, so let's suppose you have an array of numbers, and you have a single-threaded function that modifies them in some way. And now you want to multi-thread it. So you split your array up into chunks and send each chunk to the thread. Then yes, at the boundaries between the chunks, you will have fault sharing effects. But usually, if you do that, you have 8 threads or something, but you have megabytes of data, and so the boundaries are a pretty small region, right? So you still get the speed up and don't have to physically pull it out, right?
Okay, thank you.
This has been a great information-dense presentation. You showed one slide with megabytes or difference between 2 different programs, one with summation before, one with after. You were wondering what would cause that. I don't know 100% myself, but a couple of thoughts that I had was, what if the branch prediction ends up jumping across a cache line to the next cache instruction, and the other thing would be a branch prediction evicting that cache line because of Spectre and meltdown or other types of mitigations. And then another one would be, what's the different types of cache that we're working with? Were you working with direct mapping or two-way or four-way associative or other things like that? And there's a lot of complicated interplay between all of those kinds of concepts that it would have been nice if you got into it. I mean, it's really hard to go into it. So I'm really curious. Do you know of other presentations that do go into those kinds of information as it relates to cache and being friendly to cache?
Yeah, so regarding the last point, I'm not completely aware of any like conference talk or something that really goes into like the deep nuances of caches. This was like more intended to be an introduction to the like basics. Like caches exist, you should be aware of them. Regarding your point about yes, so like the first thing I expected was that maybe the basics blocks were layered entirely differently, and so in one of them you just go over a bunch of branches and the other one is in the middle. But that's actually not the case. It's like the same. It's just that the difference is just the addition instruction sort of shifts it over by one. In the one, and then maybe yes, this like weirdly spans a cache line or something, and then you have some effects. But like I haven't really dug down into it.
Can we benchmark it on different CPUs?
So like I benchmarked it on different CPUs. It didn't occur on the Intel CPU. It happens on the Apple M1. And if I do use like the efficiency versus the performance scores, the effect is differently pronounced.
Thank you.
I hate to speculate about these things, but I would look at L0 cache first.
Okay.
Anyway, could you bring up the slide where you had this one vector versus two vectors, circles and squares?
Yep. I'm gonna. This one?
Yeah, that's fine, although the benchmark results would actually be more interesting on the one with the bars. Yeah. When you did that benchmark, was the population of circles and squares in the single vector ones random, or were they like circles first, squares second?
They were random.
They were random. Okay, if you did a profiling on this, you would be able to prove me wrong immediately, but I'm going to go out on a limb and say that what you are measuring is a miss on a branch target buffer compounded by a miss on L0 cache, and it has nothing to do with D caches.
Okay, that's fair. Yeah, that could be the case. Yeah,
and
like
if you run it in the profiler, you would be able to prove me wrong or right on the spot because you would see front-end stall versus back-end stall. D cache misses a back-end stall. The address misprediction is a front-end stall.
Yeah, what I also saw were different. Like I looked at the assembly. If you have the separate arrays, the vectorization was a lot nicer than if you had the branch in the middle.
If it knows at compile time which one is which,
Yeah,
then it
yeah,
can do that.
yeah. So that's probably the main thing.
Even if it doesn't, so if you just group all the like even in your unique pointer one, if you group one type first, second type second, you would see a huge speed up.
Yeah.
And that's the branch target buffer fire.
Yeah. Yes, this isn't entirely about caches in this case. The broader point was just that this memory layout is better, and not necessarily because of caches.
Great talk. I have two questions. You mentioned that code is data, so don't make long jumps into different regions of code. And so my question there is, what control do you have over where your functions you jump into are located? And then, the second question is real quick. What is your opinion on NUMA? And can that also help you if you're copying objects to different regions, if being NUMA aware is helpful?
Yeah, so regarding the placement, so it's mostly when you have a function that does a hot loop, and then very rarely something happens. Then you want to make sure that you call a non-inline function that lives somewhere else, and it's mostly about ensuring that if you do that, like it doesn't pollute the cache, and that on the flip side, if you have something that you actually care about, that you want to execute it, it should ideally be inlined into the loop, or like you use like the section attributes in like weird cases if you like really, but like it's really a thing about like measuring than actually looking and seeing it. Like in general, you don't have any idea, but like if you have like a bunch of function calls in the loop, then right, you've got the effects. I don't have any experience with NUMA, unfortunately. I haven't gotten to play around with it.
Hey, great time. On the slide that you kind of showed, modifying the content of a picture could look like it might modify the size. I think it was slide 28.
Yeah.
Is that because of the short buffer optimization that the compiler kind of thinks maybe that data pointer is going to actually point to the vector itself and then go and modify the size?
No, it's not about short buffer optimization. It's just that the like members of the vector where it computes the size, they live somewhere in memory, and the optimizer doesn't know that data I doesn't go out of bounds of the array and doesn't reach into the memory of the thing, so it has to like conservatively assume it might.
But isn't like I would assume the compiler would consider that out of bound access as undefined behavior?
Yeah, so the optimizer doesn't know the semantics about vector though.
Oh.
Right.
Because then would you think that accessing any kind of pointer in there could feel like modifying the size? Like because at that point it's just accessing a random pointer makes compiler think that you might modify size. So if it was any pointer in there, it would have the same effect.
Yeah, so like if you write through a pointer that could reasonably alias anything in memory, it has to assume that anything in memory changed. Right.
All right, thank you.
Okay. I'm out of time. I do have 5 of the famous think cell socks, so if you don't have any socks and you want some, come by. They're L value, R value socks. So, thank you.